I'd like to open by thanking Professor Son for hosting my visit to Chicago, University of Chicago. This is my first time visiting the university. And so I'd like to begin by acknowledging the list of collaborators that have helped me push through this topic over the last 4 years or so. And it wouldn't be surprising if some of you find your own friends and collaborators in the list. And I really enjoy having worked with them. So today, I want to pursue a theme of what happens if instead of thinking about usual natural laws, you consider some hypothetical world where hypothetical conservation laws do exist, and what will the particles do in such a universe or in such a system. And the particular line of questions I want to pursue is, what if you go beyond the charge conservation, such as exists in electrodynamics, and you start proposing some higher moment conservation, such as dipole conservation? Then how will the dynamics of particles change? And one thing that immediately stands out is the fact that once you impose dipole conservation, the single particle motion that we take for granted in almost all branches of physics now suddenly becomes forbidden, because any motion of a particle implies that you're changing the dipole moment of the system, and that's no longer possible. Also, particle-antiparticle pair creation is forbidden, because what that would imply is that you're creating a net dipole moment out of nothing. But again, in a dipole conserving system, such processes are not allowed. So instead, the kind of motion that you can think of in a dipole conserving world are the ones where you form a dipole out of a particle-antiparticle, and then this dipole moves as a free particle, because that's allowed without violating dipole conservation. So why do I even bother to raise such a possibility when we know that in natural laws, such dipole conservation is not really a law? But as Professor Sonti briefly mentioned yesterday, most of what we do in physics is not really about natural systems. We create a lot of systems in the laboratories and we study their emergent properties. And I bet that's essentially what many of you are engaged in at the moment. So there's this particular physical system that interested me about 4 or 5 years ago. And that's a system of optical lattice where you have typically a sinusoidal potential created by the lasers. But in addition, you have a linear potential that kind of slopes the overall potential profile and turn it into a washboard-like potential. And then at the bottom of each potential well, you have some particles that can tunnel to the nearby potential minimum. And normally that process is very much allowed through degenerate perturbation. However, when you have a very highly tilted system, then hopping from one minimum to the other changes the energy. And therefore, and we're talking about very much a closed quantum system, so there's no real way to supply extra energy or suck extra energy away from the system. And in such an energy conserving system, it's very difficult to move this particle to up the ladder or even down the ladder, because that will violate the energy conservation. So in such a system, now what becomes the
Yes, yes.
Right. And it's presumably corresponds to rotational symmetry. It's a Newton current.
It comes from the translation symmetry.
Not translation, but rotation.
Rotation of spins?
It's a kind of angular momentum.
Not that I am aware of. The theory I know states that it's a translational invariance that are kind of responsible for this type fractonic.
So it's momentum.
Yeah.
It's conservative. This what you call D is momentum.
Yeah. You can say that. Yeah.
Because it's clear from this tensor structure of the current.
Yes.
From the second line.
Yes. So what I did to improve upon this existing wisdom was the realization is that in actual magnets, you could have more than just dipole moment. Let's say you have a magnet where the individual spins are spin 1 rather than spin half. Then, in fact, you probably remember from some course in advanced quantum mechanics that not only can you form magnetic dipole moment, but also quadruple moment. So altogether, there are 8 active degrees of freedom that you can carve out of a spin 1 object. And this number 8 also happens to be the number of generators in the SU3. Let's say you go to spin 3 half, then you can make magnetic dipole moment, magnetic quadruple moment, and also make magnetic multiple moments out of that spin 3 half spinner. And the total number of degrees of freedom is 15, which also matches the number of generators in SU4. Okay, so the reason why we normally don't think about dynamics of quadrupoles or octopoles in studying real magnets is because they are quenched. They're not active for various reasons. But from a pure theory perspective, there's no good reason to roll out this higher order multiple moments and just focus on the dipole moment. So then let's see what would happen if we allow this full-fledged multipolar magnetic moments to fluctuate in space and time. Well, the conventional treatment to study the dynamics of the magnetic dipole moment is to write down what's called the Landau-Lifshitz equation and to try to solve it as best as you can. Okay, so in the conventional Landau-Lifshitz, you have 3 components of the magnetic moments that are sort of coupled to each other. But now if you go to this higher order multipolar magnet, you have more degrees of freedom because now you have quadrupoles and octopoles are going up. So how do you generalize it? You generalize it by noticing that this epsilon tensor here is nothing but the structure constant of SU2. So if you go to the structure as constant of SUn, then you immediately have a generalized Landau-Lifshitz equation that describes the dynamics of a multipolar magnet. So this sort of generalization was suggested by a number of experts on quantum magnets, people like Christian Battista and his collaborators. So then what their generalization inspired me to think about is, why don't I apply the similar generalization to the skyrmion physics and ask myself what will happen? Again, in the conventional definition of a skyrmion current, this F used to be epsilon, which is a SU2 structure constant, but I now just replace it by the SUN structure constant. Then I go through some rigorous algebra to show that, again, no matter what this SUN structure constant is, I always recover the same, continuity equation, which implies both the total charge and the total dipole moment conservation. So it turns out this sort of higher moment conserving dynamics or hydrodynamics is rather general for not only for conventional magnetic skyrmions, but in principle for skyrmions that realize in higher order multipolar magnets.
To go to this equation, second line from below.
Yeah.
Do you use anti-symmetry?
I use this equation.
Yes. No. Second line. You use anti-symmetric property of FABC?
Oh yeah.
Or you use Jacobi identity as well. So different properties.
I don't think, we use various identities of both FABC, and also there's a symmetry combination. So we use various identities.
But Jacobi identity is a bilinear identity, F times F.
No, I don't think we had to use that.
So F is not associated with Lie algebras, right? It's not a structure constant of Lie algebra.
Exactly. Yeah.
It's just anti-symmetric objects.
Right.
Do you have the expression for Jij? I think you wrote it down earlier.
Oh yeah, it's what was it? I did write it down before. Yeah, here. Yeah, the same expression for Jij applies for any, SUN or CPN realizations. So this expression remains completely universal in a sense.
Does it still use the Levi-Civita for two indices? I mean, later you switch to 3 dimensions. Here you have a 2-index.
Well, I always work with 2 space dimensions.
Okay.
Yeah. In 3 space dimensions, all of this algebra just breaks down.
Yeah.
It doesn't apply.
So just to make sure, so roughly your 2-index tensor is partial n, right? It has 2.
Yeah.
So it has 2 derivatives. I'm trying to see how you get that. So the current the skyrmion current you started with had 2 derivatives.
Yeah.
And its divergence, it looks like there's 1 derivative too much somehow. I'm confused about the central point, which is why you can pull 2 derivatives out of the continuity equation, right? That seems to be the most important point here.
Yeah.
So the left equation, we all agree that skyrmion number is
Okay,
conserved.
so here you have only 1 derivative, so how can I pull out extra
extra,
derivative?
yeah.
That's the question. This is where you have to kind of play around with the Landau-Lifshitz equation.
I see. So it's no longer it's no longer topologically conserved. It depends
Right,
on how.
yeah.
That's
You have to
I see.
explicitly invoke the dynamics as governed by the Landau-Lifshitz equation. Okay, so now simple but rather important consequence of having this dipole moment conserving dynamics is that when you have a pair of skyrmions of the same charge, then the only motion they're able to execute is that they rotate around each other. Because that's the only way for them to conserve the dipole moment or the center of mass. If you have 2 skyrmions of opposite charges, then there's a net dipole moment going from negative to positive skyrmion. then what they do is they move, kind of move around as a free particle while maintaining the same orientation of the dipole moment. And in fact, we have seen these pictures as literally teenagers when we were learning things about Lorentz force and how that will affect the motion of electrons in a very strong magnetic field. And that lesson persists to this day in the context of, for example, dynamics of electrons in the Lows-Landau level, dynamics of electrons in the Chern band, and so on. And also I noticed a very interesting paper by Gromov a few years back. And I believe Gromov was affiliated with this department as a postdoc many years ago. He wrote a very interesting paper saying that the vortex density in a superfluid also obeys the same sort of dipole conserving continuity equation, such as written here. And in Gromov's paper, he heavily cites an earlier paper by Paul Wigman and I think Apanov, which is a rather sophisticated theory paper, which I must admit I did not quite fully grasp. But the point is that there seems to be some sort of a common theme between the dynamics of vortices and superfluids, dynamics of electrons in high magnetic field, and the dynamics of skyrmions.
Now let's know about dipole conservation.
When I was a graduate student, he made a great deal, big deal about the analogy between this, the second, and the third point, because he was worrying a lot about Bary phase effects for vortices in superfluid and superconductors. And obviously, electrons in high magnetic field also have the Bary phase effect. But despite the fact that he spent many years at Birmingham, where Tony Skyrm was like the head of the department, he never really worked on skyrmions. Okay, yeah. So regarding your question, the idea of a dipole moment conservation never really occurred to him or to anyone else at that time. Okay. Okay, so now I want to switch gears and move to the third topic. So this time, maybe it's a bit more abstract than the first two. So this concerns the theme of SPT, or symmetry protected topological order. I must say I don't really understand too much about SPT, but from my own perspective, what motivated me to think about this problem is the following. So again, citing Shivaji yesterday, when I was a graduate student, there was this big thing going on about this new concept of topological order proposed by Xiaogang Wen, and I remember the older generation were somewhat dismissive of it, but the younger generation kind of found it exciting, then we kind of wanted to work on it. And then something like 15 years ago, they came up with another sort of a notion of phases of matter called the SPT. This time, this has something to do with protection by global symmetry. Okay, so that's a kind of a big concept to swallow. And when you're confused by concepts, then the best way through is to choose a specific example and to play with it. So in my case, the way for me to understand SPT is by studying a specific toy model called the cluster state. Okay. So it's a product of Pauli X and Pauli Z operators arranged in this slightly funny fashion. And unlike the ordinary Pauli X and Pauli Z, I have a more generalized object called the Zn version of the Pauli X and Pauli Z. So instead of this qubit having only a 0 and 1 state, it can have 1, 2, 3, all the way up to n. So that this is an n-level system rather than a 2-level system. And this X and Z operators act on that n-level subspace in this way. And Z produces a certain phase factor when it acts on one of these states. Okay, so now what's unique about this model is the fact that this model commutes with two global operators or two symmetry operators. One is the product of X over all the odd sides of the chain. The other is the product of X operated over all the even sides of the chain. So if you like, you can think of this as the charge conservation among the charges on the odd sides and another charge conservation among the charges on the odd sides. So there's two separate sublattice charge conservation going on with this model. But these are, after all, some sort of a global charge conservation associated with the model. Okay, this model is sort of like the Ising model in 1D. The ground state of this model can be solved exactly and has an interesting property that when you solve this problem on an open chain, then you don't have a single ground state, you have a whole multiple degenerate ground states. In the case of Zn degrees of freedom, you have n ground states coming from one edge and another ground state coming from another edge. So the ground state degeneracy altogether is n squared. And this sort of ground state degeneracy is taken to be the manifestation of the SPT order. Okay, so this is all very well known. So, year 2022, I was doing some sabbatical at MIT, and I posted some paper on something called the dipolar Bose-Hubbard model with a graduate student there named Ethan Lake. And the day that the paper was posted, Ashwin wrote to me saying whether I would be willing to give like a presentation on the preprint that he saw the other night. And I dutifully delegated that task to Ethan Lake. And he came over and gave a summary of his work to Ashwin's group. And at the end of his talk, Ruben Veresen asked the question, what does your theory imply for SPT? So he was basically asking a question along the line of, can you have SPT order and the dipole symmetry at the same time? So that question kind of triggers some activity among the people at MIT, and we kind of scrambled around and tried to write down some version of the SPT, some version of the cluster model that is protected by, not by the charge symmetry, but some version of the dipole symmetry. So the new cluster model they came up with looked like that. And this model has two symmetries. One is the product of x over all the sites. Another symmetry is the product of x raised to the power of the coordinate. So what that really means is that this is kind of like the total charge conservation. And the second one is like the conservation of the total dipole moment in a discrete sense. Okay, so the point was that it is possible to generalize this notion of SPT to situations where the governing symmetry is not just charge, but also a dipole. Okay, so this is an SPT model. The ground state of this model is an SPT space which is protected by one charge and one dipole symmetry. Okay, that's kind of the moral lesson of our investigation.
When people say protected, it means that there are some additional, not immediately visible conserved objects.
Okay, so to be
This means
specific,
protected.
what happens with these models is that there are these degeneracies at the edges, and these degeneracies do not go away when you add perturbation to the model, as long as that perturbation does not break the symmetries. So within that kind of a space of Hamiltonians that preserve the symmetry, then you kind of have the same universal feature happening at the edge, and that gives you a sense of robustness to the notion of this phase being protected by the
So
symmetry.
not just arbitrary conservation laws, but those laws which survive deformation of the model.
Yeah, so the perturbation has to be consistent with the symmetries. See, the idea is that if your perturbation breaks one of these symmetries, then this thing immediately goes away. So it's not as robust as a topological order, which remains robust under all symmetries, all perturbation. Okay. So you can even take this idea one step further and write down some cluster models protected by quadruple symmetries with total charge, total dipole moment, and the total quadruple moment. And if you
So is translation symmetry important for this modulated SVT, or is
yeah, we do assume translational symmetry.
but if you break translations, these are still non-trivial, or
Let me see. Yeah, yeah. If you break the translation, I think we did some simulation to that effect in our paper. If you break the translation by introducing some staggered perturbation, the SPT order survives up to a certain point. Yes.
Question. So if I sort of zoom out and I look at, like, I think these were like Zn spins, if I remember correctly.
Yeah, yeah.
So it seems like there's some unit cell of size n or something.
Yeah.
I mean, if you look at this.
Yeah.
So if I just put all those degrees of freedom and thought of that as just one site, one super site.
Yeah.
And would it be, it looks like it's sort of what might reduce to a regular cluster state with some regular global symmetry Z2, in the
Yeah.
first case Z2 cross Z2, and in this case, or Zn cross Zn in the first case, and maybe here Zn cross Zn cross Zn or something.
Yeah. The point that we have tried to make, and also others have refined the argument, is that it's not quite like that. So the point is that this dipole SPT is not some ordinary SPT on a larger unit cell. It's different. There are some, for example, you can do some cohomology considerations that can tell you what's the proper classification and so on. There are some papers by Hota Lam which does that. Yeah, for details, I guess I want to refer you to those papers. Yeah, so now the final point I want to cover is this idea of non-invertibility. And this was pointed out in the context of the cluster model by Shoheng Shao, the winner of this year's Breakthrough Prize, New Horizons Prize. And what he noticed in the context of the cluster model, he studied the Z2 cluster model, but his observation generalizes immediately to Zn. Was the following: in addition to those two global symmetries that I mentioned, two charge symmetries, there's one more symmetry possessed by the cluster model. So if you look at this cluster Hamiltonian, and you swap x by z dagger z and z dagger z by x, then the model is invariant. But what does this transformation look like? It looks like the good old Kramers-Vanier duality, so-called duality transformation. But then what they also pointed out is that although this is a symmetry of the Hamiltonian, K is not a unitary operator, in the sense that when you multiply K dagger with K, you don't get a 1. You get something else. And this was rather puzzling because I, like many of us in this room, have heard about Kramers-Vanier duality from textbooks. And the first proposal of Kramers-Vanier duality took place in 1941, so it has been around for 90 years or so. And the fact that people didn't realize the non-unitary nature of this transformation was pretty striking to me. I mean, how could we have missed this for so long? So then I got interested in this problem a little bit from about 2 years ago. Then I tried to come up with sort of a poor man's version of why the Kramers-Vanier symmetry or Kramers-Vanier operation is non-invertible. Okay, so first of all, it is possible to write down the Kramers-Vanier operator explicitly. It's given in this way. But let me give you a more pictorial representation of the Kramers-Vanier map. The Kramers-Vanier map takes you from one many-body state. So G is a collection of Zn spins to another many-body state G prime with a phase factor given by this number, where omega is the nth root of unity. So on the operator level, you can write down the Kramers-Vanier operator in this way. And the Z2 version of this form first appeared in a paper by Fendley and collaborators about 10 years ago. And the Zn version of this appeared in a paper by Masahito Yamazaki, the person we talked about over lunch, about 2 years ago. So that was very useful for me. Now, what the Krams-Vanier does is actually much easier to understand when you think of what it does on a quantum state or a wave function. So suppose you let this Krams-Vanier operator act on some many-body state. So the action can be interpreted as changing the wave function, original wave function psi s, to a new wave function psi prime s, related to the original one by this transformation rule. Okay, but then when I write this expression down, it looks a lot like something we know very, very well, which is just the Fourier transformation. Okay? So what the Fourier transformation does, you take some wave function and you multiply that with this kind of phase, and then you sum over all the initial degrees of freedom. Right? That's what Fourier transform does. Now, what I show on the left side is the Krams-Vanier transformation, and what I show on the right side is the Fourier transform. And yet, now you see the only difference between the two is that the sort of the target variable in the case of Fourier transform is just a spin. But in the case of Krams-Vanier, the target variable is a difference of two spins at the adjacent sites. Okay, so think of these spins as being arranged on a one-dimensional chain of length L. And instead of taking the value of the spins at the site J, you take the value of spins, difference of the spins at the nearby sites, and use that variable to perform your transformation. And that's exactly what Krams-Vanier does for you. Now, this change of variable has an interesting and obvious consequence. Namely, now that since the target variable is the difference of spins, when you sum that over all the sites, these spins cancel each other out, has to sum up to 0. So that's a constraint. And now because the target variable has a constraint, what will happen is that under the Krams-Vanier transformation, the mapping is not going to be 1-to-1. It's more like n-to-1 mapping. And therefore, it's no wonder that the inverse map cannot exist. So for someone like me who does not have a lot of heavy math background in category theory or whatnot, this interpretation is really helpful in seeing why this Krams-Vanier transformation is not invertible. It's simply because of these constraints in the mapping. So in light of this a simple mathematical observation, now you can think of the conventional Fourier transform as the charge Fourier transformation, whereas the Krams-Vanier is kind of interpretable as a dipolar Fourier transformation. And if you have a charge in a dipole, you can take one step further and consider a quadrupole Fourier transformation, which is a transformation where the target variable is like this. You know, this combination basically represents some sort of a quadruple moment. And now, if you did the quadrupolar Krams-Vanier, then the new target variable has 2 conservation laws. Therefore, target space is even smaller. So now you can mathematically envision this whole hierarchy of Fourier transforms with charge conservation, dipole conservation, and any sort of multiple conservation. And only the charge Fourier transform is invertible. Okay, so I think my time is up. In summary, I tried to sort of envision an alternative world or engineered world in which you have more than charge conservation. And in theory, at least, it's certainly possible to construct such theories for classical systems and quantum systems and whatnot. And as a kind of a cute byproduct of this investigation, we arrived at the interpretation of this well-known non-invertible symmetry, namely the Kramers-Bonnier transformation as kind of a dipolar version of the Fourier transform. And I find that kind of amusing. I just want to share this little insight that I had with you. Okay, so thank you for listening.
So one way to think about Kramers-Bonnier, maybe the more old way of thinking about it, is it's unitary within the subspace that's symmetric.
Yeah.
So does your higher, I don't know, generalizations of Kramers-Bonnier, are they unitary transformations within some space?
Yes, exactly.
Vanishing dipole moment and
Yeah.
I see.
Yeah.
So another way people talk about Kramers-Bonnier is like gauging the symmetry.
Yeah.
So when you do this multipolar, are you gauging both the charge and the dipole
Yeah.
at once? Is it possible to gauge one but not the other? Or
I don't think so. Yeah, I think you have to gauge both simultaneously.
you drew this analogy between electrons in a magnetic field and skyrmions.
Yeah.
So is there also like lowest Landau level physics? Or
Yeah, I think there should be, but it's not obvious where it's coming from. Okay, so in the case of vortex dynamics, there's this idea that when you move like a particle around the vortex, you pick up some phase, which you can interpret as the Berry's phase effect. And Berry phase effect can be interpreted as some sort of emergent magnetic field sitting there. So the question is, in the case of skyrmion fluid, do I also have some notion of an emergent magnetic field? I think there is, but it's a little bit difficult to point my finger at something, some mathematical object, and say, hey, this is playing the role of a magnetic field in the skyrmion system. I haven't been able to put my finger on something specific yet.
Thanks. So this is the lowest Landau level, but the feeling factor is very small.